Okay, let's now start with this. I want to welcome everybody once again to this workshop. This week we'll be looking at correlation and linear regression. And let's quickly look at the timetable. I don't think that we should waste time on introduction because almost everybody here, we are familiar with one another. So I think we should just proceed. If you are not, maybe want to get to know somebody more as the workshop progresses, you get to know people more. So we'll quickly look at the timetable. 3 days, within 3 days, I believe that maybe the first day, we look at correlation, and the other 2 days will be on regression. If we cannot finish on correlation today, we can finish up to tomorrow. But I think we should be able to finish correlation today so that by tomorrow and next tomorrow, we focus on regression. Though they are related, we'll still be making reference to correlation. Now, we'll be looking at understanding the concept of covariance because that covariance is important to origin of correlation. Then correlation, you will see that is the standardized covariance. And we'll get to know why correlation is the standardized covariance. We'll look at how do you measure the correlation using correlation coefficients. And those are anything we're going to be calculating, their correlation coefficient and the types. Because if you want to run with SPSS, we tell you which type of correlation you want to do. It's different from the coefficient. The coefficient I is talking about, are you looking at two variables or another one is coming, so we'll be talking about different types of bivariate partial. Then the following day, tomorrow, we'll look at linear regression, the origin also, and method of least square, because that's what the logic behind is this method of least square, and assessing the goodness of fit of after that method of least square to plot the regression line. We want to, how do we assess it? You discover that while we are doing that, regression is the same thing as ANOVA. We're going to see that ANOVA is one of the methods to assess the goodness of fit. So ANOVA is just part of regression. So coefficient of determination, and that one also you see, it takes us back to correlation, how it relates to regression when you look at the coefficient of determination. It's quite different from coefficient of variation, so that I won't be confused. Though we talk about coefficient of variation when we're talking about mean, standard deviation over mean. You know, if we want to compare variability between different variables, because they don't have the same unit. You cannot just use variance, cannot just use standard deviation of variance alone. So you must be able to, because they don't have the same unit. But if you now divide the standard deviation, the variability over the mean, and multiply by 100, that is coefficient of variation. It's different from coefficient of determination, which is the one we want to look at here. Then regression coefficient itself. Then the third day, we're going to realize that it's not, you can, even linear regression is about predicting quantitative continuous variable, but independent variable can be anything, can be categorical, can be anything. So whenever you want to use categorical variable regression, any form of regression, even if it is logistic regression, you need to create dummy. So how to create dummy variable? We'll do that, and then how do we now? Because the essence of the reason many people want to learn regression is how to control for confounder. That is using multiple regression. That will be the last thing we do. By the time we are done with it on Sunday, everybody should be confident enough to say, okay, you can run regression. So that's it. So Dr. Udo Zima, you're welcome. Jane, you're welcome. So let's just proceed.
Thank you, sir.
Yeah, good evening. Yeah, good evening. Yeah. So let's just proceed. So I've just discussed the timetable, what we'll be looking at in the next 3 days. Okay.
My people are on the field, but they may be joining later this night.
Okay, no problem.
Able to join today, we'll join tomorrow.
No problem. No problem. Okay, let's quickly look at correlation. That's what we're looking at today. And we are all familiar with the word correlation. The usage, the way people, any other person, apart from the researcher, use correlation is different from the way the researcher uses it. But it's very funny that, well, you know, I've discussed under the logic of scientific reasoning that the biologists, when I say biologists, mean doctors, all those in medical line, and generally biologists, maybe life scientists, needed statistics more, or need statistics more than physical sciences. You need statistics more than physicists and chemists. Then social sciences also need statistics. So it's biologists, the biological science and social science that need statistics more, because most of the variables, the phenomena you study, they are not stable. They vary a lot. There's much variability. Most of the people that contributed to development of statistics were biologists. In fact, specifically they were genetics, like Fisher, like Pearson. They were biologists. They contributed a lot. There are some social scientists also contribute a lot. Statistics, the word correlation, the way researchers use it. In fact, I think maybe it's only the biologists, especially the medical line, and maybe some social scientists that actually use it most appropriately the way it's supposed to be used in research. But you see many other research, other fields, when they do it, they say that try to correlate. They just use the word loosely. But you get to know that the way the word correlate or correlation in ordinary English is quite different from what it is in statistics, in research. Let me say statistics, because in research we have different field and different field of research. So people do whatever they like. If you see, remember, there is a study design called correlational study, and it's only in epidemiology, it's only in health, it's only in health. It doesn't exist somewhere else. And what we call correlational study, what we call descriptive study is what some other field they call correlation. Once they just one group, they say it is correlation, they are doing correlational study. But the word in epidemiology, we say correlational study, it's a study design. We also call it ecological study. And actually the meaning actually portray the meaning of correlation really. So in everyday life, correlation reduce the volume. The correlation denotes some form of association. There's an association. So that's what correlation means. But it may not be quantified. Then in statistical terms, we use correlation to denote association between quantitative variables. That one has to be there. Association between two quantitative variables. Association between two quantitative variables, that is correlation. So the two variables you are dealing with, you must be able to put value, number on them. Though originally, some variable may not have number. For example, ordinal variable, like when all the like SK, when you are trying to know the severity of disease, you just rank 1, 2, 3, 4, 5. You give it. Those are not the original value. It's just for ease of analysis, you just put value. You do correlation, so because in as much that you have put value, you can do correlation. But the type of correlation is different from the correlation we do with something that is continuous variable that naturally it has numerical value. But it's still correlation. But when we get to different type of correlation, we iron that out. But just know that correlation, there's nothing, you cannot correlate two things that don't have numerical value. It's not possible. You're going to see the description of correlation will make you to understand that. Then We also assume that the association is linear, that one variable increases or decreases a fixed amount for a unit increase or decrease in another variable. What correlation mean? Yeah. Association between two variable, quantitative variable. As this variable increase by certain unit, this other variable may increase or decrease by certain unit. So if A increased by 2 and variable B increased by 3, another increase in variable 2, A by 2, then this one increased by 3. Another increase by 1 in variable, that one increased by 1.5. So the issue there is that there's a fixed amount of increase whenever one increase. Then it may be decrease. It doesn't have to increase. So that we're going to talk about different type, whether it's positive or negative correlation. So we talk about that. But just know that there's a variation, that is a value increase changes, there's a corresponding change in value of this. So it has to be quantitative. So it has to be something that has number. So otherwise, you cannot talk about correlation. Now, regression involves estimating the best trend line to summarize the association. You know, you're going to see that regression is another step ahead of correlation. There's an association. Then for you, though correlation quantify the degree of association, but regression does something, because it's not association that has much meaning, has relationship. Not all association you observe, but there are some association that have relationship, and that is what regression go further to determine value of one from the other. Just like as we are here now in this lecture, some people you are meeting for the first time, there's an association in the sense that they say that, oh, you have been in the same lecture for 6 months, or you are attending the same lecture. That's an association. But it doesn't mean that there's a relationship. But of course, if there is a relationship between two people, there must be a form of association also. It's just like somebody that if two people that are husband and wife, of course, it's a relationship, because in a relationship you determine there is role. Each person has different role in the relationship. So for the case of husband and wife I'm talking about, you see that there's no relation with that association, because somehow they will be seeing you together. You will be doing something in common, even before it even culminates in marriage. So I use this illustration or something that it doesn't make meaning, because this is mathematics we are talking about. But I just use the mathematics to explain the social issue, to explain and actually make meaning, because that's what it is. Now let's move on. Now let's quickly look at association and reversal relationship, because many issues, because the correlation we are looking at is measuring degree of association. Is looking at the strength of association, the strength of association. So if you say the strength of association, by the time we go further, you'll be able to understand very well. The correlation is completely symmetrical. Symmetrical in the sense that if you say a correlation of A and B is also the same thing as correlation of B and A. So it doesn't matter which one you call first. No, it's in the sense that that is why when you are talking about correlation, there's nothing like dependent or independent variable. There's nothing like say, oh, this one comes first, this one lead to this. No. If by the time you want to talk about that, you are moved from the realm of correlation, you are going to the realm of regression. And the reason is very simple. It's not all variables that correlate, that have anything in common set. It's just a coincidence. Maybe confounder and many other things. Just coincidence. It's just like, for example, you say the rate of drowning. As the rate of drowning increases, then the rate of ice cream sale increases. All does ice cream have to do with drowning? Maybe something in common, maybe it has to do with season. Maybe around the season people drown, the season high cream cell. But the issue is that if you collect data, happen to collect data of ice cream and drowning and many things, you will see that if you just run your analysis, just like especially if one is doing survey, you have many data, community. You run your analysis, you will see that drowning and ice cream say they correlate strongly. So, but it doesn't make sense. It's only when there is sense in it, okay? If there is a relationship, two things can correlate and there is a relationship, then regression will now determine the value of one from the other. But on a normal note, correlation, you cannot say one depends on the other. So it's just more like a crude way of looking at strength of association. That is why it does not mean causation. But the fact that two things correlate does not mean this is what is causing it. In fact, I thought it's far from it. Now, if two variables are related, that's a relationship. It means that when one changes by a certain amount, the other change on their average by a certain amount. So, though in correlation also, you are expecting change, but in relationship, of course, one change, one determine the other. We'll talk about that. This relationship is more to the regression side. If Y represents the dependent variable and X independent variable, this relationship is regards as the regression of Y on X. Can you see? So whenever you are looking at two variables, if there is the first crude way of assessing association is the strength of association, which is I'm talking about two quantitative now, which is correlation. But by the time you want to move further to know if there's a relationship between them, that if you can determine the value of one from the other, then you are going to regression. Now, let's quickly look at how correlation comes. Because the first person that described it also was the first person that described chi-square, Pearson. And that is why the commonest chi-square is named after him, Pearson chi-square. And this correlation, so the commonest one, which is the most, that is the first description of correlation, the Pearson correlation coefficient. So how did Pearson get to understand? These intelligent people think. He was thinking, and you're going to see how correlation came from covariance. So let's quickly understand covariance. For you to understand correlation very well, you need to understand covariance. What is covariance? It's a measure of how much two random variables vary together. When you say vary, that is vary in value, together. So variance is similar to variance in the sense that variance means a single variable varies. When you say what is the variability? The measure of variability we know, variance, standard deviation. That is, when we talk about height now, how does height vary among the population? That is the variance or the standard deviation or weight or whatever. But for covariance, it's not talking about two variables. How do they vary together? Can you see variance talk about one variable, single variable? How does it vary in the population? While covariance talk about how do two variables vary together in the population. Now, this one is just a picture, but this same picture go for correlation, but at the basic level, just look at it. If two variables vary together very well, let's say perfectly, and in positive direction, when you say positive direction, it means that as one increases in value, the other one also increases in value. It's always like that. If it is always like that, perfectly, you can see that if you put one on vertical and put one and try to look at the value, that's just way. But when you are talking of two variables, let's say assume that this is this one vertical. As the values increase, you will be moving along the vertical and the value of the. So the way the two of them meet, that is the point you are putting. So you can see this thing be on a straight line means that both of them, as this one increases, this one is increasing also, like this, perfectly. But this one, this first one, it means that as one, can you see, one increases, the other one decreases. Can you see? Look at where this one and this one are. But this one was a low value for the horizontal, but high value for the vertical. As this one becoming high, this one becoming low. So that shows that as one increases, the other one decreases. So you can see the slope is negative. That's why it goes down. This one go. When we are talking of moving toward the right side. You know, when you are writing, also you are writing, you are moving from left to right. So if something go down from left to right, it means it's going that the slope is negative. If something now go up from left to right, it means that it's increasing. So this number 3, this third one, that is increased. Both of them increase together. Why? This first one, if one increase, the other one decrease, or if one decrease, the other one increase, they move in opposite direction. So the one in the middle show that there's no pattern. They didn't vary together. There's no variation. That they don't vary together. Not that they don't vary, they vary on their own, but those two, they don't vary together. That's one near zero covariance. So if covariance is degree to which two vary together, this middle one, no, they don't vary. Two variables don't vary. That's why you cannot see a pattern, just scatter. Now, let's illustrate variance and covariance now. Now, this is an example. We have 5 people. They watch adverts of a particular product. And after watching adverts, somehow, maybe the adverts, it created a desire in them to buy some packet of product. So this data says try to see how the number of adverts watched by each person or by people vary with the number of packet bought. You see, this first person, number 1 person, watch 5, bought 8. Second one watch 4, bought 9. This one watch 4, bought 10. This one watch 6, bought 13. This one watch 5 and watch 8, bought 15. And you can calculate the mean number of advert watch. If you add all the 5 together and divide by 5, here is the mean. This is standard deviation. This one for the packet bought. This is the mean standard deviation. If you plot it on graph, just to create a picture, the blue one is the advert watch, the blue line, the blue graph, and while the green graph is the packet bought. You will see the mean, the line you are seeing horizontal are the mean for each of them. You remember for the advert watch is the mean is 5.4. Look at the bar here between 4 and 6, so you can see it's 5.4. While for the packet board, the mean is 11. Can you see? Then you see the value of each of the, how do they now vary from the mean? How are they apart from the mean? So of course, for the first 3 advert watch, the value 544 are below the mean, which is 5.4. That is why you can see how they are below. So what you are seeing there is minus 0.4 is how they differ. Why they carry minus is because they are below the mean. So how do they differ from the mean? 0.5 by 1.5. You can see 5 from 5.4 from 5 minus 0.5, 0.4. So you see, then the last 2, 6 and 8, they are above the mean. That's why, can you see? And they are how much? Because they are above, that's why we carry positive sign. So the same thing goes for the packet, but the first 3 are below the mean and the last 2 are above the mean. You can see the pattern that because these first 3 are below the mean, the first 3 also below the mean. The last 2 of the advert watch are above the mean. These ones are above the mean. So it shows a pattern that both of them vary together in a positive direction in the sense that as one increases, the other one, they go in the same direction. You can say, categorically say that as the number of advert watch increases, the number of packet bought increases. If you were to be the opposite side, if as the number of advert watch increases, the number of packet bought decreases, what will happen is that these first 3 that are below the mean, the corresponding bought will not be below, it will be above the mean. the corresponding packet board, the value will be above the mean. And this one that are above the mean, the corresponding packet board will be below the mean. So that shows that these two will be facing them, and why this one will be away. If let's say it's in opposite direction. But if they don't even co-vary at all, if they don't co-vary, you will not see any pattern. You can see this one may be here, this one may be here, scatter. You cannot say, oh, one is facing the other one is away from that one. Just see random scatter pattern. That shows that there's no covariance. That's just a way. How do you compute it? That's just a way of illustration. How do you compute? That's what I want to explain. How do you compute the covariance? Now, you remember the formula for variance. We usually denote every variable as x. But if you have two variables you are dealing with, you can say one is x, one is y. If you have three, you can say one is x, one is y, one is z, whatever. But since most of the time, if you are dealing with one, just say x. So variance, as you know, how do you get? Variance is mean square deviation from the mean. Deviation from the mean is x minus s bar. That is, you remove mean from the x. X bar is the mean. X is the value of each. So s bar. You square it. When you square it, you calculate the average by dividing by the degree of freedom, which is n minus 1. So variance is sigma. That is addition. When you addition of square deviation from the mean, then divided by the degree of freedom. That's why we call it the average square deviation from the mean. Average square deviation from the mean. So I think we will not talk much about that because this is not supposed to be a basic one. Because we have talked about. I want everyone to go subscribe to the video, the lecture video. We are there. Just subscribe through our net, internet, and our website. You see all those things that I explained there. Now, this sigma x minus s bar square can be written as x sigma x minus x, then x minus s. Because it's just, you square it now. If this is x minus x bar, it's just deviation from the mean. So deviation from the mean times deviation from the mean. So you can write them separately like this. So it can still be written as sigma x minus s bar, then in times x minus s bar over n minus 1. So this is variance. The covariance, since they are now having, there are two something. All you need to do is to substitute, because it's not only one that is varying now, it's varying with. So if there are two variables, one can be denoted as x, y, one is denoted as y. So one half of it will be this one. Simple. So this is called formula for covariance. Just from the variance you can see, this is formula for covariance. So it's not only one variable that is varying now, it's varying together with another variable. Formula. So if you now, I just computed it here, x minus s bar, y minus y bar, multiply add everything. The sigma, the addition is 17. 17 over 4. You know the degree, n is 5 is n minus 1, 4. So the covariance there is 4.25. Now, you may say, why should I be? Hardly will anybody ask you to even calculate covariance or you do covariance for anything. That's why, apart from the fact that maybe some people are even hearing it for the first time, or maybe you just you've heard of it somewhere when they say analysis of covariance, multivariate analysis of variance, and COVA, analysis of covariance. So you may hear it from the bed that to say just covariance is hard. The reason is very simple. It's not going. Instead of being used, it's correlation that is being used. So we are going to how covariance correlation replace it. Now, problem of interpreting covariance. Now you will see from that formula, x can be anything, y can be anything. Imagine if x is weight, y is height. Well, it will give you value. Whatever you are feeding in depends on the unit of measurement. Depends on the unit of measurement. Height, if the weight is measured in kg, you know what I mean? The human being age. For if it is adult, you'll be talking of 70, 60 something, 80 something. Those are the weight. Well, if it is height, if it is in meter, you'll be talking 1 point something. Can you see? But if you decide to measure the height in centimeter, you'll be talking of 170 something. Can you see? So whatever you get here, the covariance, the value depends on the unit of measurement. If you change the unit of measurement, if you change it, okay, but the fact that you change, you want to look at covariance, how height and weight vary. So if you use, you decide to use meter, what do I call it? Meter here. It will give you different value than when you use centimeter. That one, that's apart from that one. If what we are comparing now, want to see what vary together is the distance and time. Distance, travel, and time. If this one is kilometer and this one is hour, so covariance you are going to get will be large, because when you are talking of this and you are talking of 1,700 kilometers, 2,000 kilometers. While this one, maybe the time will be talking of 12 hours, 24 hours. So you see that covariance now, whatever you get, depends on the value you feed in and the value and the unit of measurement. So you can compare covariance now among data sets with different units or scale of measurement or different variable. So the weak covariance is one data that said maybe is a weak covariance is one data set may be strong in another one. So the main problem in interpreting covariance is that the wide range of results it gives, because you can't even, if we are not talking of other things that have big units, can give you thousands, while something that has one small unit give you small. So the larger the x and y value, the larger the covariance. So the value of that variable depends on what comes out. Similarly, the larger the unit of measurement, for x and y, the larger the covariance. So how do we face the intelligent people? How did they face the problem of interpreting covariance? The problem was faced by dividing the covariance by the standard deviation of x and y to get the correlation coefficient. Now, this logic is the same logic they use to produce this Z distribution, Z score, that give the standard normal distribution. And those intelligent guys, people like Pearson, were the one that did all those things in those days. Now, what did they do? You remember what they did in producing standard normal distribution? What they did was, okay, they discovered that yes, many things follow normal distribution. Yes, height, weight, blood sugar, distance, travel, IQ, different things. But those different things have different units. If you have to plot normal, it's the same shape, but you what to plot will be based on the unit you use. So intelligent people now, okay, the best way to do it now is that instead of representing each, like let's say weight, I usually use weight for example because it's common thing you know of. Let's say weight, let's say you look at weight, instead of you using, oh, Ugo, you weigh 70 or 75. You want to say, okay, does your weight differ from the average weight? How many standard deviation you weigh? So if the average weight among the population is 70, it's an example, and the standard deviation is 10, it's an hypothetical example, and you go weigh 80. So all you need to do, okay, remove 80 from 70. It give you, remove 70 rather, 70 is the mean from 80. It give you 10. That shows that Ugo is 10 kg above the mean. And the standard deviation happen to be 10. So when you know how many standard deviations you go away from the mean is 1. Because if you just divide that 10 by 10, it shows that what is captured, the difference between Ugo's weight and the mean weight is just one standard deviation, because the standard deviation is 10 kg. So the person that weighs 60 will be 10 standard deviation different also, because it's 10 kg different. But in opposite direction, there is lower. If you remove 70 from 60, it gives you 10, minus 10. So it's one standard deviation also, but it's minus 1. So minus in normal distribution does not mean the value is minus. It just means that that particular value is showing you to the degree to which it's less than the mean. So minus 1 standard deviation in that sense, in that data says 60 kg, plus 1 standard deviation mean 80 kg, plus 2 standard deviation mean 90 kg, minus 2 standard deviation mean 50 kg. So that is how they discover, they invented this Z normal, standard normal distribution, now called it Z score. So instead of you to represent you by your value, he represents you by your Z score, that is the number of standard deviation away from the mean. So by division, you have removed unit, because if you look at the illustration again, the denominator, the difference between the mean weight and the weight of that person is in kg. You divide by the standard deviation, is in kg. Kg cancel out kg. So whatever you have, that Z score is dimensionless. It's a ratio. A ratio is what you get by dividing two quantities of the same unit. So it has no unit. So it's the same thing here. So the intelligent people now, division. Let's divide this covariance by the standard deviation of the corresponding value. So if X here is weight and Y here is height, so you divide their covariance by the standard deviation of weight and height. So in that case, you have cancelled out the units. So it's not standardized. So whenever look at it now, correlation is standardized covariance. That is, covariance divided, and that's it. Look at the covariance, we now divide by the standard deviation of the two of them. When we divide it, look at it, this is what you get, which is the formula for correlation. So it can be written this way, just to try to calculate so that it make it faster, so do the same value, the same thing, give though it look complex to understand, but if you use this formula, it give you the same answer. But just look at this, that is the formula for correlation, and it's covariance over standard deviation. Can you see now? Covariance is still the element, the numerator of covariance is still the numerator here. If you look at what is here, is the numerator of the standard deviation of each of the S minus S bar square, no square root with this, that was the Y. So you can see, you divide covariance by standard deviation of S and Y to give you correlation. One thing with it is that correlation does not have unit. I've already explained, because it's the same covariance of, let's say, weight and height divided by standard deviation of weight and height. So both weight and height, they are in numerator and denominator, they are cancelled out. So it's a dimensionless quantity. And correlation is not affected by changes in the center or the scale of the variable. So you don't need to, either it has something to, it's universal, just like the Z score. It's universal in the sense that, it's used in engineering field, used in biological field, in any field. So you notice something, most of the things that you get by division is universal, because the unit will have cancelled out. That's why something like relative risk, odds ratio, all those, they are universal. Chi-square also, the way you calculate it is, if you look at it very well, it has no unit. That's why you will not say chi-square and output unit. No, anything you see doesn't have unit. It's a ratio that has been calculated. So when you use, even if you are in engineering, you say the weight of the concrete, but somehow the denominator weight of the concrete will be there. So weight will cancel weight. So the same thing, if somebody is using surgery and you look at the the width of the heart of the back, and so the division also, the width of the back will be there. So at the end of the day, that particular entity, this statistic we can call it now, is universal. That's what correlation is. So we have established the fact that correlation is a standardized covariance. Let's move on. But before we move on, I want us to ask questions. We want to move on now to start describing correlation. So any question? But that's the pattern, because I don't want to wait till, because you may have questions you want to ask. Any question? Or is it simple? We proceed. Who is using? Okay, it's Prof that is using iPad. Professor Wakwe. Professor Wakwe. Okay. Any question? Okay, as you proceed. Okay. Are you hearing me?
Yes, sir. Yes, sir. We're here, sir.
Okay. Okay. Let's just proceed. So let's continue. Meaning of correlation. So correlation is the degree of linear association between two variables. The strength of the association is summarized by correlation coefficient. And the correlation coefficient is a dimensionless quantity ranging from minus to plus 1. Now, you know, that particular, the formula we just got now for correlation, you notice one thing there is that the numerator can never be greater than the denominator. You know, when numerator is greater than the denominator, that what you have will be more than 1. The numerator can never be greater than the denominator. So the worst or the best that can happen is that both the numerator and denominator is 1. Is the same in value. In that case, the correlation will be 1. That's the highest. Any other thing, the numerator will be changing, reducing. If the numerator is 0 over the denominator, the correlation will be 0. So the value ranges from 0 to 1. But it can be in opposite direction. It can be in one direction or the other. It can be positive or negative. So for positive correlation, the one that has positive sign is what we know as direct proportion. To remember your mathematics in secondary school, we talk about variation. Direct two things, they have the directional, directly proportional to one another. As one increases, the other one increases. If one decreases, the other one decreases. That's directly proportional. That is the counterpart of positive correlation. When two things, they are directly proportional. So the proportional, the variation, that's mathematics. But in statistics, it's correlation. You want to talk of variation in mathematics, it's correlation. You're going to see that statistics is a branch of mathematics. But most of the people that develop statistics, they develop it out of necessity. They are not even mathematicians. As I've said before, the early developer of statistics were people that needed it. They were biologists, social scientists. Of course, now you can call it it's a branch of mathematics in the sense that it's a formal science, just like mathematics, because that is root in mathematics. Borrow a lot of things from mathematics. Like for this one and this relation, correlation in statistics. So direct proportion is positive correlation. The inverse proportion, whenever something increases, the other one decreases, that is negative correlation. So I usually use example. Most of the people that attend the class, most of you are science students. Remember your physics, chemistry, Boyle's law, Sharp's law. Those Sharp's law talk about the pressure of gas being directly proportional to the temperature. As the temperature increases, the pressure increases. If the temperature decreases, the pressure decreases. So both pressure and temperature move in the same direction. That is direct proportion. That is positive correlation. Boyle's law, the other way, Boyle's law talk about the volume and pressure. As the volume increases, pressure decreases. As the volume decreases, pressure increases. So volume and pressure are in opposite direction. So that is inverse proportion, which is negative correlation. Just make it simple like that. So a positive correlation is one in which both variables increase or decrease together. Or a negative correlation is one in which one variable increases and the other decreases. Now, when variables are exactly linearly related, the correlation coefficient equal either +1 or -1. What this one just means that just know that whenever it is plus, it's direct proportion. It is negative, it's inverse in opposite direction. But the strength now, so because the negative, the sign has nothing to do with the value. It just, so whenever you see +1, it's combining two things. It gives you the type of correlation, then the value is the strength. Now, the strength, when you say something, if it is 1, that shows that always, as this one increase, this one will increase. Or as this one increase, this one decrease. Always is perfect. That is, they are linearly related perfectly. Correlation coefficient is unaffected by the unit of measurement. I've said that one because it has something to do with unit. So when you say you are correlating distance and time, it has nothing to do with the unit. So if you can do it for distance and time, you can do it for weight and height, you can do it for length. It has nothing to do with the unit. You can see the formula because it is as cancel out unit, the formula. Now, the square of correlation coefficient gives the proportion of the variation of one variable explained by the other. This one, don't be silent about it. We'll talk about it in regression. That's what we call coefficient of determination. I will talk about regression. Now, this is just to show in a pictorial form scatter plot. The scatter plot is just to show, if you look at it, I showed the same thing for covariance. But now we have done away with covariance. All things are past. Everything is new now. Now, for correlation, it's the same pattern anyway. Look at this. This is this one here. Perfect. Is going up as one increases the other one. Because this dot is where each point meets. So as it's going up like this, it shows that as this vertical one increases, the horizontal one decreases. These are just showing two variables, one at vertical, one horizontal. You put one horizontal. And you can, in correlation, anyone can be at vertical, one can be at horizontal. It doesn't really matter. So as one increases, the other one increases perfectly on the line. That shows that the correlation is 1 plus 1. If you go to be negative, -1, the slope will be like this. It become negative. Now, look at this one that is negative. Look at the slope. Though it's not perfect, it's 0.8 because it's scattered. But you can now see that they are on a line. It's still they are moving on a line. But in what is showing that as one increase, the other one decrease because look at it. Look at this first dot now. It's here at the starting point for this horizontal, but it's at the higher point for the vertical. As this one is increasing, the value of the vertical is decreasing. It shows that as one variable increases, the other one decreases. If you want to move from this one now, this dot, last dot here, is at the high point of the horizontal and the low point of the vertical. Can you see? As the vertical increase the value now, this one decreases. So it's whichever way. So in a negative correlation, as one decrease, the other one increase, or as one increase, the other one decrease. Look at this one, it's positive in the time, though it's more scattered than it. That's why the correlation is 0.3. But yes, you can still see a line. But look at this one. Can you see? Once you cannot pinpoint, is it going up or going down? I don't say it's scattered like that. Its correlation is 0. The same thing. Look at positive correlation, positive perfect correlation, negative perfect correlation. Curve line, curve. Sometimes this one curve linear. That is, this one it can happen some correlation. Though as if horizontal is not a straight line, it's curved. But you can see as one increase, the other one increase, but not linearly. Now look at this. Okay, yeah. Ayo. So, correlation coefficient. You know, the one we just give me 1 minute. Just a minute. How are you? Yes, I'm back. Yes. The one we just described from covariance now is actually Pearson correlation. There are many coefficients because most of the time, many advancements in statistics start with quantitative variable, majorly continuous variable. So what Pearson described was through covariance was for continuous variable. Well, after that, some intelligent people also came to devise means of adapting the same thing to variables that are not continuous, that don't follow normal distribution. So the first one, Pearson, is also called product moment. Product moment just means the multiplication it does. If you look at it, just multiply if you look at the numerator, you multiply the division of one variable by division of another variable. The denominator is the standard deviation of one with standard deviation of another variable. So that's what we call the product moment correlation coefficient. So it is more appropriate, it's represented as half. It's more appropriate when you are dealing with continuous variable. When you say require interval ratio data scale. This is what interval ratio. You need, those are the, scale, it's talking of scale of measurement. So those are the things. If you go and watch the video, you'll be able to watch the video of the former initial lecture, you'll be able to get clue about that. Then Spearman rank correlation. So this sort of put rank and Kendall's, both of them are rank correlation, in the sense that a data set that does not follow normal distribution, like majorly ordinal variable, like SK, anything just give 1, 2, 3, 4, 5, or it can be to any better. It's rank data. You cannot use Pearson correlation. You can use Spearman correlation. Kendall also the same thing. But it's more appropriate than Spearman in the situation where the sample size is very smaller. Then we now have a lot of tyrant also. What we mean by tyrant? In a situation where you see you are trying to correlate maybe you have something 1, 2, 3, the particular score, something on the like scale. On the particular score, you see a lot of people having, the same value, 2, 2, 2. They know you can put something on like scale 1 to 5, demo, and you discover that more people score 1 than the other. So that is higher rank. Then we also have point biserial correlation and biserial correlation. Now, these last two are very, very interesting in the sense that it allows a quantitative variable to associate with something that is categorical. No, we've already said that correlation is linear association between two quantitative variables. Then you can have a situation where you say you are correlating sex and blood sugar. The sex is a categorical variable. The sex is dichotomous variable. So is when you say category, it has to be dichotomous now. Dichotomous means two categories. No, for sex, I say that male or female. Now, you now see that when you look, let's look at this point biserial and biserial. The biserial, point biserial talk about association between a continuous variable and a discrete dichotomous variable. Discrete dichotomous variable, no continuum on the line. Dead are alive, male and female. Then look at this second one, a biserial correlation coefficient, quantify association between a continuous variable and a continuous dichotomous variable. A continuous dichotomous variable, there's a continuum underlying the two categories, passing or failing an exam. So I want to stop. I want you to ask questions because I know that you have questions. I want you, because this one, I want us to discuss it. This last two, point biserial and biserial. I don't know if there's any question. Any question?
I'm not very clear with the continuous dichotomous variable, because the example you gave, the bar is covering the down part of my distance, so
okay.
I cannot see the last part very well.
I will do that. Just wait.
Yeah, I can see now.
I want to drag it up so that it was, yeah.
So, continuous dichotomous variable, passing or failing, how is it continuous?
Okay, what I want to do is discuss that sometimes, it's a workshop, even though it's a virtual workshop. I want a level of interaction. That's why I did that. But so how do you not differentiate this one from me? This one say a discrete dichotomous variable. Wait, is a discrete dichotomous variable. No continuum underlying the two categories, e.g., dead or alive. This one I talk about a continuous dichotomous variable. There's a continuum underlying the two, passing or failing an exam. So I want us to differentiate between the two.
Well, it's actually straight. It just means that for the point biserial, you're having, continuous. We know just variables, they take decimals. While the discrete, in the discrete, they have an underlying coding of either 1 or 2 or 1 or that's they have numbers underlying. Now the difference between this one and the biserial correlation coefficient is that this one, the association is between a continuous variable and so there's a dichotomous variable, but the dichotomous variable is not taking 1 or 2. What is taking on is actually numbers that carry decimals. It's like in the of let's say you have dichotomy. Let's say you decide to have a range. It depends on maybe the clinical variable we're looking at. If it's blood sugar now, let's say you've splitted your data. That is the I don't know, what's the word?
Cutoff. Are you talking of cutoff?
That is the part where it becomes diabetes, and the part where it becomes non-diabetes.
Okay,
Let's say
okay.
you say, oh, 1:6:2, then 1:6:2. That's just the explanation for the biserial. It's dichotomous. It's two, but it's continuous on decimals. So that's just difference. Thank you.
Okay, thank you. Let me just explain it. It's not because I thought you were trying to explain it better. You know, you didn't get it right anyway. When you say this point biserial that I talk about, if you look at both of them, is looking at association between continuous variable and something. Both of them have maybe continuous variable, maybe age. Then you want to compare with this first one, discrete dichotomous variable. Dichotomous just means there are two possible, dead or alive, male or female. There was no number, continuous variable underlining. For the passing and failing exam, before they say somebody pass exam, he will have scored a mark or fail an exam. So, like if you say diabetic, before you say somebody is diabetic, there's an underlying blood sugar that you now have a cut of anybody that have blood sugar 126 and above is diabetic. You're like passing an exam. Anybody that score so and so pass, above pass, or failure. Anybody that score below this fail. So all those passing or failing exam, blood sugar, diabetes or nobody, obese, not obese, they are continuous dichotomous variable because there is underlying continuum under the two categories. Is it clear now? Why the other one, dead or alive, male or female? There was nothing like that. Is it clear now?
It's clear.
It's clear, right? Is it clear or is it clearer or is it clear?
It's clear. It's clear.
So it's very
It's
clear.
clear.
So it's very safe. So
please, sir.
Yes.
Hello, sir.
Yes.
Sorry, sir. That point by serial you just mentioned, you know, because when you were teaching us that Thursday, because you know, even if it's dead or alive, you were saying that it cannot be nominal, it cannot be dead or alive. It has to have an online number.
You didn't. You see, you are
there has to be an underlying code.
You are missing.
That's dead or alive.
Listen to me. You didn't get it. You are missing up. And one of the things that sometimes if you are in a lecture and maybe that's one of the things, maybe you are doing house short, you may miss, once you miss a sentence, you may misinterpret. The issue of putting number, when you want to run correlation, you are going to create dummy. I said something at the beginning, I don't know if it's to the end. I said that when I was going through the timetable, anytime you want to use categorical variable.
Yes, sir.
I even say for regression, for it goes for the same thing that happened here. Categorical variable, you have to create a dummy. Yes, I'm not. So even the point bacteria want to do now, for you to use dead or alive to do correlation of male and female, you must code one category 1 and the other category 0. Yes, I'm not. You must code one category 1, the other one 0.
Okay.
So that is what maybe that was what you misinterpret. What we are saying here, bacteria, discrete dichotomous variable, somebody dead or alive, is not based on maybe there was a number before. Somebody male or female has nothing to do with number before. So there's no underlying continuum. Continuum means there are number, continuous variable underlying it. But if you talk about diabetes.
Okay, sir. So this, maybe I didn't explain it well. Because you know the way on SPSS, we have dead. That is, we can write dead or alive in the data, but in the variable view, we code it as 1 or 2. That's the underlying code. So are you saying that in the act data view, we have to, instead of writing this dead or alive, we write it as 1 or 2 in the data view?
Listen to me. You are only required to code something 1 or 0 when you want to use it for regression or we want to use it for correlation now. If you want to use
Okay.
it for correlation, something that is categorical
Okay.
before, it's something that is not number before. Yes, I'm now. If you want to use it
Yes.
for correlation or for regression, you have to code it 1 or 0.
Yeah. Yes.
That's why you create dummy. That's why if the tree has 3, if the tree has, if you want to do regression now, if the variable has 5 categories, you have to now create 4 dummy for 5 categories. You want to hold one constant and create the other one, put a 1, 1, 1. When we create dummy, see the way it goes. We do creation of dummy either tomorrow or today or tomorrow. We create, look at it, not today, tomorrow we create dummy. Tomorrow or next tomorrow, we create dummy.
Okay. Okay.
So if that one has nothing, this one is talking of, it's not a matter of you entering data now. They are just talking that variable, this dead or alive. Was it based on a particular number before? Is it when somebody has blood sugar above so or blood pressure above so and so that is dead or alive? No. Dead or alive has nothing to do with number. Yes, I'm not. Male and female has nothing to do with number. Yes, I'm not. But if you look at the other one, the biceria, that 2 category was based on number. It's a cutoff they use, like anemic, not anemic. So if you want to do, you say you are correlating weight on anemic and not anemic. Weight is a continuous variable. Anemic, not anemic, is dichotomous variable. But that type of this thing is a biserial correlation in the sense that what inform anemia is you have done hemoglobin concentration or PCV and say a value less or equal to this is anemic. The other one not anemic. Yes, I mean now. The same thing with blood sugar. You did blood sugar. Is there anybody that scored 126? Blood sugar is continuous variable. But anybody 126 and above is diabetic. So if you now have your category diabetic, yes or no, and you now want to correlate that yes or no with something like blood pressure, which is continuous variable, that is biserial correlation, because that anemia, yes or no, diabetic yes or no, or obese yes or no, they were based on figure before. It's a cutoff. They were based on continuous variable before.
Okay.
That is why they are continuous dichotomous variables, as opposed to discrete dichotomous variables. Does it make sense?
Hello.
Yes, I'm listening.
Hello.
I can hear you.
Hello. Hello.
Who is talking? We are hearing.
Hello. So can you hear me? Okay.
I can hear you.
Okay. At some point, I wasn't hearing you. Maybe it's my network. Thank you very much, sir.
Okay. Now, any other question concerning that? Let's proceed. Now, this is Pearson, and this is the Pearson correlation, the one we have derived from the, what do we call it? Covariance. Now, we have an example computing this Pearson correlation as a data set pulmonary dead space. So somebody to share it. Okay, before you even share, let's quickly look at it. Before you share and run it. So this one is trying to correlate the height of children with the pulmonary dead space. So maybe Dr. Odo Shima, Shima should explain pulmonary dead space to us, because we are trying to correlate the height of a child with the pulmonary dead space. So that people that are not everybody are. So everybody is a pediatrician. So let her explain to us what that pulmonary dead space means. Hello, see there? Dr. Uzo Dima. Oh, is not there. Hello? Okay. Let's continue. So let's say these are the value 1 to 15. There are 15 children, 1 to 15, and these are their heights in centimeter. And this is sum of the 15 height. And this is sum of the 15, and this is the mean. Now, if you add everything together, you divide this sum by 15, give you this mean. The same thing with the pulmonary dead space. Each of them has its own pulmonary dead space, and this is the sum. This is mean. Now, if you follow the formula we are talking of, all you need to calculate is the x at the height, the y at the dead space, then x minus s bar. You remove x bar, which is the mean, from the x. For each of the 15 of them, look at the answer. Remove y minus y bar. And you remove y bar, which is the mean y, from each of the y, give you this. So what do you need? You need to multiply the two, x minus s bar as y minus y bar, before you sum it. So you now multiply this and this, what we have here. Now, if you look at the denominator, we are looking at x minus s bar square. This x minus s bar, you square it. That is, you square it, give you this. Y minus y bar square, square it, give you this. These are the sum. Then, because for the x minus s bar square and y minus y bar square is their sum, well, after summing them, you need to have their square root from this. So that's why the square root is here. So the summation of x minus s bar multiplied by y minus y bar is what we have here as numerator. Can you see? So when you want to calculate r root now, it's got to the numerator, which is this 5426.6 over the square root of this, which is 72.46792, times the square root of this, which is 88.48126. This is the correlation. So the correlation between pulmonary dead space and the height is a strong correlation, 0.84631. So before we move further, let's run it. So let's run it. There's a data. The data set I sent.
Can I run it?
Eh?
Can I run?
Yes, you can do that. You can share.
Okay.
So you can. We have opened it. Share it.
Which one is the data? Which of?
The name is pulmonary dead space.
Dead space. Okay.
Pulmonary dead space. It's not. What's happening?
Height and pulmonary dead space.
Eh? Yes, height and pulmonary. Yes. Height, exactly. And what's happening? Can I share? Who else can share? Jane, do you have your own? Because I sent to everybody.
No, I have it. I'm just this.
What is the problem? Share. If you open your express, share the express. I can tell you how you go about. If you open the express, first of all, share the express. Once you are open, share the expresses. And even if you go to the where the folder is. Just double click on it to automatically open the SPSS if you have version 125. Where is the, okay, Dr. Bako? But this thing, okay, so it started sharing, but why is it's like your network is slow? Dr. Bako? Dr. Bako? Dr. Bako? Let me share it because
blocking my view.
what is blocking? What is blocking your listening?
There was one of these, these annoying pop-ups. I now have the, okay, the data is on.
Yeah, I'm hearing it on Papa.
Hello, sir. I'm back, sir. Sorry.
Dr. Bako?
I have,
Yes, sir.
I have the data now.
Don't you have the, share the data now? Share if you have the,
Can you see it?
it's coming up. We have seen
All
it.
right, good.
Yes, we have seen it.
It's all right. Thank you.
Yeah.
Sorry about the delay, sir.
Okay. So this is the, if you look at that data, that's what you have here. This is just serial number.
Should I explain pulmonary death space?
You want to explain to us?
Yes.
Okay, explain.
It's just, normally when the body takes in oxygen in the pulmonary system,
Yes.
there's an exchange of oxygen for CO2 at that alveoli cell level. But what the dead space means is that it is that air, that portion of the air that is not involved in that exchange. So, from the bronchi, all those other parts of the airway that does not get involved in. That's what the
Okay. It's the alveolar level that gets exchanged.
Yeah, that's and even within that alveoli, there are some of them. Not all the oxygen, not all the air gets exchanged.
Okay.
Because that the air inside, they're just responsible for.
Yes. Okay. Because I wanted to check it, I forgot. I didn't have time to. Because sometimes also when you are doing that, it's good for you to understand what you are doing, but it makes more sense.
I agree, sir.
Not just running data. Okay. Now, you cannot see, though you know that if you are to talk about this space will be the y, will be the dependent variable, while the height will be the independent variable, because the dead space will depend on the height of the child. Okay, now let's go now. Click on analyze. Want to do?
Okay.
Now
I've done that.
Correlate. Go to correlate. Move down.
Correlate.
Under the mixed model, you see correlate.
Yep.
Bivariate.
I
will come and explain this.
Okay.
Yes. Bivariate.
This one?
Yes.
Okay.
I will still explain that one. That bivariate, what it means.
Okay.
It's like slow.
Okay, it has opened.
It has opened.
Because I really want to do it.
We have seen, yeah. So just move the two to the variable. So the two, height, emitter, and pulmonary death space, move the both of them.
Pulmonary death space. Okay. They are both there now.
So if you look at it by default, Pearson correlation is what is there, checked there, where candles and Spearman are just.
Yes, sir.
So it's Pearson you just want to do. Click OK. And he said that 2T, that is 2T by, now say flag the correlation, just leave it like that. That if it's significant, you flag it.
Okay.
Down, back, it has nothing to do. It's not even useful. Okay, click OK.
So do I share?
So share the result.
And I clicked OK. You can't see the results.
No, you cannot. You have to share it.
How do I do that? Do I
stop sharing it and I share the result? Because if you try to share again, you may not get it. Okay. You have shared the result after you have.
All right. So tell me when you can see it.
We still waiting. Okay, we have seen it. You
Okay.
can see now. You see, correlation usually and the software arrange it in matrix, because if you are doing more than maybe you are having many variables you put in now, that's how it will arrange it.
Yeah.
Arrange it. Can you see? This one height, pulmonary dead space along the vertical, height, pulmonary dead space along the horizontal. So if you see the first cell now, it's correlating height and height. Of course, it will be 1. If this second one, it correlates height and pulmonary dead space. Can you see? This is what we got, 0.846 when we calculated. And this one is correlated, see, pulmonary dead space and height. It's the same thing. Yes, I'm now. So why this one, pulmonary dead space and pulmonary dead, it will be 1. So it will arrange like that. The where each variable correlates with itself, it will be along the diagonal, put 1, 1. While the real value you are looking for will be off the diagonal. Which are these? Can you see? But one will be the mirror image of the other. It's just one you just pick. So you see, the p-value is very low, 0.00, means that it's very low, lower than 0.01. And I already said that nobody use p-value to interpret correlation, because it doesn't make sense. Because if the sample size is very large, a big correlation, a small correlation will be significant. Even if the correlation is 0.1, to be significant, 0.01, very small, to be significant if the sample size is very large. And if the sample size is very small, a big correlation may not be significant. So because of that, nobody use correlation p-value to explain, to interpret it. We rather interpret and say the correlation is strong or weak or negligible or perfect. So I don't know if there's any question concerning this. Is there any question? So if there's no question, you can stop sharing. You can stop sharing, yeah. So if there's no question, let's move ahead. Now.
What I wanted to ask is that what is the cutoff between the weak and the strong? Is it 5? Is it 0.5?
No. Okay.
0.5.
Is
that the cutoff between weak and strong?
So look at it. Is where different people have a reference, but I will look for the reference. This one I use it. Anything 0.
We can okay. I can see what you are doing now.
Is 0, no correlation. 0 is no correlation. Is less than 0.2, negligible. Negligible. That is very small. Then 0.02 to 0.5. Might. Then 0.5, maybe to 0.49. Then 0.5 to 0.8. Moderate. Moderate. Then 0.8 to 0.99. Strong. Strong correlation. While 1, perfect. Can you see now? So that's how to interpret it. So I will look for one for a reference so that I will include in the slide. So you don't interpret it with significance. That's no meaning. That one has no meaning. Okay, let's proceed. So sometimes you may want to test for the significance, whether the association is merely apparent and you want to test for the significance. Though if we run as regression, if we bring the t for us, you see the value to be there. So if you want to test for significance, to tell whether the association is merely apparent and might have maybe due to chance, this is the, that r just t is equal to r square root of n minus 2 over 1 minus r squared. So all you just need there, can you see, is the n sample size. In this case now is 15. Then the correlation you have gotten, which is 0.846. So it will give you 5.72. So if you want to do the same thing, if you want to check this one now, if you want to check that t-test, that check if this correlation is significant. So we'll go share again, share that thing again. I will tell you what to do. You run this as regression, you get, share it again. We want to see if that correlation is significant. But we already said that the significance has nothing, though the p-value is already there. But if let's say you want to check it with hand, because if you look at it when we run, they want to look at t-test. Yes, the t-test. Yes. So for you to do the t-test, you have to run this as regression. Yes, I've seen it. Yes, we have seen it. Go to analyze. Analyze. Analyze.
Then what's the next thing?
Is it network?
Hello?
Yes. Go to regression. Regression.
No, I've done it.
And go to regression.
Okay. I'm there already.
Click on linear.
Linear, okay.
That's you just
I'm
want to
already.
not doing regression. Okay, move pulmonary the height as the independent and pulmonary as dependent. Yes, pulmonary dead space dependent. Move it as the first, yes. Move height, yes. Great. Just click OK.
Okay. I have to stop sharing.
Okay. So you have done a share the result now.
I see.
It's coming. Yeah.
Hello?
So yes, we can see it. We can see. Scroll down. Where we are looking for, scroll down. Scroll down. Scroll down completely. There is still is the last part of the result we want to do.
No, I'm already down.
And you can see the T. Can you see T? The last table on coefficient. You see T. You see for height. You see under the height. Because that first one is constant. But I will not explain it now because it's when we do regression, we will explain. But just see 5.72. Is that not the result we got in the other one? If you use hand, that's the T. Can you see? Can you see now? And look at the p-value, the same p-value you get. The one though in the SPS they have already they didn't put T there. But when they run this relation, they put the p-value there. Yes, I mean now. They put the p-value there, but you don't get T. They didn't. But T, what do you need it for? But in case you want to, this is how you get the T for it. So you can stop sharing. Does anybody have question concerning that? Because I don't want, we are not looking at another part of this. Is when we get to regression that we talk about whatever you get from the regression. But just for you to see how you get that T out. Okay. Dr. Bako. Dr. Bako.
Yes, sir.
You also prepare to share anytime.
Yes, sir.
Okay. Now, let's look at the sperma correlation. It's an alternative way. So when you are dealing with quantitative descriptive, such as number, like number of children now, sometimes it may be appropriate. Number of children is a discrete variable. Though it's a quantitative variable, it's not a continuous variable. No, it doesn't have decimal. Number of anything. Then other categorical such as Likert scale, like pain score, all those Likert scale you use. So Spearman is better. It is a non-parametric procedure due to Spearman is to replace the observation by their rank in the calculation. So in the calculation on how do you compute it, we look at the way you compute. That's Spearman. You look at the same data set. This height and pulmonary dead space. So how if let's say you want to use Spearman, you want to calculate Spearman for it, rather than maybe it's a data you want to calculate Spearman for. Look at the way you do it. You rank the height, you rank the dead space, so you rank both of them. Can you see now? So you can see then the difference between the rank. Like this one now, we remove this from this. It doesn't really matter which one you remove from which, because by the time you square the negative, D is the square. It will cancel out any negativity. So you remove one from the other. Here now we'll just remove the rank for height from the rank from the dead space. So these are the value. When you square it, it gives you. When you add the square to get the square D is this. So look at the formula. The formula for the rank correlation is 1 minus 6 sigma D square all over M to N square minus 1. If you look at it, the only thing that is not constant you are looking for is the D square, because N means the sample size. That's all. So if you look at it now, the D we got, D square is 60.5. When you put in, it gives you 0.892. If you look at it, the Spearman correlation is a little bit for this thing, is a little bit higher for the rank correlation for the same data, set. Because the other one is 0.846, that is 0.892. So let's run it. Let's run the data. Dr. Babagana, you can share, if you have not shared, you can quickly share the data. It's the same pulmonary dead space.
Okay.
Height and pulmonary dead space, yes.
It's coming up.
Okay.
Is that height and pulmonary dead space?
Yes, height and pulmonary dead space.
All right. Yes, sir.
Okay. We have not seen. You share now?
Are we there, sir?
Oh, you can't see now. Have you shared?
I've shared though.
No, we are not seeing. Are you sure you share? You have to click on share screen.
I think my network is a bit faulty.
Okay, no problem. Maybe we go still share your own and let's use it, because it's the same data set. Okay, it's coming now. It's coming.
All right.
Yes.
Is it the same thing, sir?
No.
All right.
This one is another data set too. This one is for the one is something like that one is for regression.
Okay, let me just.
Height and pulmonary. That's the one you share is death rate. You click on that height now. This one, yes. Is the death rate you share?
Height and pulmonary.
Yes. This is not. Maybe you have opened it before.
It's the same thing.
No, Cannot be. It cannot be. It's not the same. Look at it. Look at the title now. Look at, you can see. You can see it.
Yes, it's possible.
I think it's
Hmm.
maybe you have opened it before. Ugo, you can share your own. Share the same. The height and permanent. And let's click on the. You just want to click
I
on the
have
schema.
files, about 5 of them.
It's like you have opened it before. You have opened them before. Hmm?
Hmm. Nice.
Dr. Igulu, are you there?
Yes, I'm here. You want me to share?
Yeah, share, yes. Share it again. Share the same data set. Yes, that's great. So just go to the same correlation. Go to the same correlation. You just know there is an option where bivariate. Then, yeah, if you look at it, click on the sperma. You can even click on the candle also. Click on the sperma candle. So let's just do the three together. You see this. Click on the candle also. Okay. Okay. Click OK. Yeah. Yeah, share the results. Yes. You will see, you scroll, no parametry. Can you see? Candle, tau, and this thing. So if you look at it, what we just calculated now is 0.892, right? For candle, that's what you're having here. It's 0.892. While the other one, the tau is 0.746. Let's note it because the way to calculate that one is different. That's for candle. Okay. I think you can. Any question? Is there any question on this?
My only concern is just that we are using it for practice, but ideally the data is not suitable for this.
Don't worry. Maybe
because they are not,
yes. Don't worry.
the
I have
data
a
is not
data
suitable.
set. Tomorrow, I will be. Tomorrow we're going to use it to do this candle and this thing. I have a data that is not. It's only I have not sent it. I'm trying to put it in. So, all this data also is it's not easy to just get a data and that will comply with a data set that comply with what you are looking for. The see also is the logic that matter. You get it?
I understand.
The logic here.
I understand.
If you look at you have calculated those things, they have a data set. We'll go to calculate the candle and the sperma. We can do that one first thing tomorrow before we proceed. Yes. Any other question? Okay, it's very clear. Let's proceed. You can stop sharing.
Lisa, I was trying. So there was something. Okay,
Go
maybe
on.
my network is delaying my
We can
question.
hear you now. We can hear you. We can hear you.
Okay. Okay, sir. Thank you, sir. I was actually trying to find out that formula because I didn't get explanation because you were breaking the one about the T. You were explaining formula for them.
Is it the one for T test for correlation?
Yes, that's the sperma. That one will show T equals to
The sperma. Okay. The sperma is
yes.
where how they derive is one complex better 6d square over n into n square minus 1. Okay, let me show you. Just stop sharing. Let me show you. I will still share this slide with you. You see the formula there is very. Stop sharing. Yeah. Look at it now. Can you see it?
Okay.
1 minus
Yes, I
C
can.
sigma d square over n into n square minus 1. N is the sample size. Like in this case now is 15. And
Okay.
the only thing you are bringing in
Okay.
is the d square, which is the square of the difference in the rank of the two. No, you rank the two. Can you see? You rank the two. You now look for the difference. You minus 1 from the other. You now square the difference. That is the d square. And that's the only thing you put in the formula.
Okay, that's the difference. Oh.
That is the difference.
Okay, so after you found difference between the two ranks, you now squared it.
Yes, square the difference. So in that case now, it doesn't really matter which one is even higher than you. Once you know, if you find the difference, you are going to, if you remove 1 from A from B, it will be different from remove B from A, because some may give you negative. But to remove that thing,
Yes.
by the time you square it, it has removed it. It doesn't really matter which one you remove from which. The d square will be the same.
Okay.
The d square will be the same. If you look at it, you notice something in statistics. When you do a difference, most of the time, that difference is not useful. It's you square it. The logic behind it is to remove the effect of that negativity. Can you see?
Okay.
Yes.
Okay, yes, sir. Yes, I understand. Yes, sir.
Hello, sir.
Yes, sir.
Hello, sir. Yeah, how do we use it for, in the case of Likert scale calculation?
It's the same thing. Okay, I have a data set. I will share that one tomorrow. We'll do it first thing. It's the same thing, sir.
Okay, sir. Is it the one that you say agree, disagree, that?
Yes. You know, you disagree, like I say, the one, you give you 1, 2, 3, 4, 5, or whatever.
Yes, sir.
Some reach 7, some reach 3. But you cannot have like a scale less than 3, because anything 2, 1, 2, it's not a scale. Before you can say something is ordinal, it must have at least 3 categories, right? Anything 3 categories and above. Even so now you can have up to 10. You know, there are some things you can put on a scale of 1 to 10. So, but you start from 1. Charlie start from 1. So we can use it. So all you need to do is to rank the score. And okay, don't worry, I'll give a typical one tomorrow, so that, because if you remember when we did non-parametric counterpart of t-test, when there is a tie, if you look at this one, any tie rank, you share it among the group. If you look at this one now, you see that the difference, if you are ranking pulmonary dead space, you see that 56, 56. I'm coming. I want to read it. If you are ranking pulmonary dead space now, you see that 2 people score 56, 56, 56. Can you see? And it's supposed to be number 5 and number 6. That's why you now have 5 and 6, 11. Now divide by 2 to share, and now become 5.5, 4.5. Those are the value that tie among the pulmonary dead space. Yes, I mean, even when you don't worry, when we get tomorrow, we'll use one particular one that is rank this. You see the way we do it. Any other question? Okay, there's no question. Let's proceed. Right. Yeah. Now, biserial and point biserial. So this one also is a little bit tricky, but okay, the one I wanted to show before is, because I was putting on the slide, is the tout also. The tout, okay, I will explain that one later. The tout is just that one, just C minus D. It's just like the formula we use for, what do I call it? McNema. C minus D all over C plus D. That's all. That's for the tout. The C is the concordant, D is the discordant. Okay, let's just continue with this one. I will explain that one together what I want to do tomorrow. Biserial and point biserial correlation is actually the square root of the proportion of cases that fall into the larger category and proportion of kids that fall into the smaller category. You know, when we talk about biserial and point biserial, we talk about two categories. We code one as 1, you code one as 2, as 0. But it doesn't really matter. But the issue there is that one will have higher category, one will have lower category. But it doesn't even really matter because if you look at the P and Q, just the proportion that fall into larger category will be 1 minus proportion that fall into smaller category. It's just like when we calculate our sample size, say P, Q is 1 minus Q, and Q is 1 minus P. So at the end of the day, the square root then over Y, that's ordinate of normal distribution at the point where there is percentage of the area on one side and Q of the other. This is where you use statistical table to look at normal distribution. If the percentage is maybe 70-50, you look at the Z that correspond to that junction of 750. Of course, you know that if the thing is 95.5 now, you already know is one thing is going to be the thing is going to be 1.645. But you have to check the table of normal distribution to know that. But know that the biserial coefficient is calculated by running basic correlation. Because the issue there is that the one side, one of them is continuous variable and the other one is what do I call it? The other one is categorical variable. There's a data set among the one we have used before. I want somebody, or less, if you cannot share, I will share it myself. What with the data set on Ebola victim? I think you have it. I think Dr. Babagara, you have it. Okay, your this thing was giving you problem. Maybe I should just share it myself. Or Ugo, you have it now, the Ebola victim. You may not know where it is. Let me open my own. Let me open my own.
Okay, I was already trying to check for it, sir.
Yeah, it's under me. Where we do our me. It's where we do our me. That's the last thing we did now. Me. When we talk about me.
Okay.
Yes, when we look at t-test rather. T-test.
Okay, yes, I have it. Let me open it.
Yes, one sample t-test. That Ebola victim. One sample t-test. That's
yes, I've seen it. Do you want me to share?
I share it, yes. Let's use it for
Should I share?
Yes.
Okay.
Because there we coded sex as female 1 and male 2.
I've seen it, sir. You had 0 and
exactly.
When you can see, just tell me.
We can see it. So let's do the correlation now. You go to analyze. We want to correlate age and sex. Can you see now? So you look at it now. We have already coded the male to be 0 and female to be 1. Correlate, bivariate. Now move both age and sex in. Yeah, just click OK. It's piercing you are using. Click OK. So share again. You have to share the result.
I don't know if you can see.
Can you see? Yeah. Yeah. So if you look at it now, you say there's no the 0 point something. There's no correlation between. Can you see the result? Everybody can see the result.
Yes, sir.
So there is no correlation between. It is 0 correlation. Maybe if the decimal continue, maybe it will be 0.00, but that is very no correlation between age
and sex.
What we have just done now is a point biserial correlation.
Wow.
point by serial.
Point by serial.
If let's say we have this, though, if you look at it, the logic between it just name the biserial point by serial is the same thing, but the name and the description just for you to differentiate the underlying factor. Because if I want to do it for maybe blood sugar, I've already said diabetic, not diabetic, and I correlate with age. The computer does not know if it's because I already coded 0 and 1 also. I don't know if you understand me now. So it will run the same thing. So any question, you can stop sharing.
Okay, sir. Thank you, sir. I actually have a question. There was something you said. You said that like if you had done diabetes and non-diabetes, that the computer would, like I didn't get that statement.
Computer wouldn't know where you got it from. Whether there's underlying continuum. What I'm just telling you is that the description between the differentiation between point by serial and biserial is more like academic, just to know the underlying factor. It does not go into the analysis. That's what I'm telling you.
Oh, I see.
Because you are correlating continuous variable with categorical that you have coded 0 and 1. So both of them is like that. It's only that for the point by serial, the category are discrete, dichotomous. While the biserial, that 1, 0 you coded, that 2 category was based on some continuous variable before you coded them. But when you are not running the analysis, the computer will not know and doesn't need to know that. So let's proceed. So no question. I know that, well, if you understand it, that's very good. They expect you to be confused anyway. Now, you will see that by tomorrow, what we just do is that I will still just revisit some things about the candor and spearman. I share another data. I will be rank data that we're going to use. But I will still want us to run. I have some other file that we're going to use tomorrow for regression, multiple regression. But we're going to do correlation now because the one we just did now are just 2 groups. But 2 variables you put in at once. But you can have multiple variables. How does he arrange it? You're going to see. He's arrange it in a matrix. You're going to look at it. But this one is a form of summary. No, for you to know which type of correlation should I do. Because sometimes when they bring data, you have to use brain to think of which one should we do, which one should we do. Is it a person or spearman or kind of data type, categorical. If it's categorical, if it's continuous data, it's normally distributed. If it's normally distributed, you do piercing. But if it's not normally distributed, that should that is not parametric. So you now decide if it is ordinal. Well, if it is continuous before and it's not normally distributed, it cannot be it cannot be ordinal variable. So it will now use spearman and use around correlation. But from the beginning, if let me go. If the data set is categorical, you now come, okay. Is it ordinal? You know there are different types. Ordinal, of course, that's where the issue is. Actually, for you to even do non-parametric, something that is categorical, you use correlation, it has to be ordinal. You cannot do the one that is not ordinal because, for example, you cannot correlate ethnicity for what? Because ethnicity, you cannot even accrue value because it's nominal scale. I don't know if you get it now. It's nominal scale. The only categorical you can accrue number to correlate are ordinal, ordinal. But in another way, A discrete variable, not actually categorical, like number of children, you can decide to use sperma. Don't want to use person. Number of something. Use. So you discover that whenever you are correlating, when the two variables are continuous, or one is continuous and one is discrete dichotomous or dichotomous variable. Of course, and the continuous variable follow normal distribution, just use pairsing. It is when that particular variable that is not normally distributed that you now use pairman. But if you are dealing with discrete variable, because it cannot be normally distributed, use pairman. But when you are dealing with ordinal variable, use Kendall. And you can use sperma for ordinal variables. So basically that when the ordinal variable, the sample size is very small and there are a lot of time, Kendall is better. But hardly do people use Kendall. People use either pairsing or sperma. Now let's quickly, you remember when you wanted to run the analysis, you saw something like bivariate. Let's look at type. We have, we've discussed the correlation coefficient. But when you want to do correlation between two variables, how does it come? It comes in three types. The commonest one is bivariate. Bivariate just means that there are two variables involved in the correlation you are computing. Now, a third variable may come in. We have already said that correlation, strength of linearization between two variables, quantitative variables, two variables. Now, sometimes a third variable comes in because you want to remove effect of confounder from the two for the correlation you are looking at. Now call it partial correlation. For example, if you correlate the number, the number of class attendant, the percentage of attendant in class, you correlate with mark score. If you do that, that's bivariate correlation. But sometimes there is some underlying factor, like the number of hours a student study can affect the score. And it can affect the attendance also. Many people that read very well, sometimes overread self and they may not even decide not to come for the lecture, for a particular lecture if he has read it. Then some people also, they read a lot and it will affect the score. So if you want to remove the effect of the score, of the time of hour from both the attendance and the score, you now do partial correlation. Then if you are removing the effect from only one of them, maybe from the score, you don't believe that the effect should be effect on the attendance, but on the score, that would be semi-partial. So before we close, I want us to go back and I want somebody to share. Okay.
Before you move away from that slide, could you explain the bivariate again?
Bivariate is just the one we have done now is bivariate. The one we have even run is bivariate.
Okay.
Don't worry. What we'll do now is that we want to run now. I will explain the bivariate. I will explain the partial also. I want us to go and rerun. But we are going to choose a file that has more than two variables. The one we have been more than two variables. So we can share that particular, there are some files there. Death rate is there. Systolic blood pressure is there. That's true. Somebody should share death rate. Who has the data? Jane, you didn't download those file I sent? Hmm? Jane? No, yeah.
Okay, sorry, I was muted. I'm downloading it now. It will take me just a minute.
Okay, let me I share my own. Ugo, are you there?
Which of them, sir?
Yes, sir. Let me share.
Death rate. Yes, you can share. Death rate.
Okay.
Yes. So these are if you go to variable view, variable view, so that you can see the explanation of this. Click on variable view. Yes. So this first one is death rate per. You can expand it that place. Then the second one is availability of doctor per. Expand that label space so that people can see what is written there. Yes. Drag it to the right. What is happening? Okay. Then hospital availability. Can you see? So yes, it's okay. It's okay now. It's okay. So death rate per 1,000 residents. Then the second variable is doctor availability per 100,000 residents. The third one is hospital availability per 100,000 residents. Then the fourth is annual per capita income in thousands of dollars. And the last one is population density per square mile. So you can correlate all of them at the same time. Okay, let's go to analyze, because all of them are quantitative. Go to analyze. Analyze. And you see all of them are number. By variant. Move all of them inside. You can say Control A and move everything. Just say Control A and move everything. Yeah. Click OK. So share the results. Yeah. Can you see now? So you see that the way you brought them in, death rate, doctor availability, hospital availability, annual per capita income, population density. The way it arranged it vertically is the way it also arranged it horizontally. So you see along the diagonal is when each of these variables correlate with itself, like death rate, death rate. Of course, it will be one when the same thing correlate with itself. Doctor availability, one. Hospital availability, one. Annual per capita, annual per capita, one. And the last one, population density, population density, one. So, but off the diagonal, so what you have here is mirror image of the other side. So when you are even putting it, just one you choose. So if you look at it here now, doctor availability and death rate. Can you see the correlation is you expect the correlation to be, I don't know for them, it's supposed to be negative correlation. Is it minus I'm seeing, or it doesn't have minus? So in fact, can you see, suppose this one is positive correlation, though it's very small, but it's supposed to be negative. Then look at hospital availability and death rate. Then annual per capita income and death rate. negative. Can you see? So what is it that if the income increases, death rate will reduce. So population density and death rate, negative correlations. It means that the population density, but it's supposed to be positive. Population density increases, death rate decreases. That's what it's showing. Then look at here. It's looking at this. Okay. Can I show my annotation so that?
Fact, yeah, I think it makes sense because it's actually supposed to be as doctor availability is increasing. The death rate is supposed to be decreasing.
Yes, but it's not, that's not what it's showing.
I don't understand.
Because negative correlation is supposed to go on negative. And that's what the data say. You know, it doesn't matter. A good doctor availability may be there, and you may see that, especially if the doctor are specializing, and you know that it may be reason for that.
Yeah. If you look at it carefully, if you look at the the availability of hospital now is the one that has the decreasing death rate.
Increase both doctor and hospital. And you know the funniest thing is that increasing something does not mean that its service get to people anyway. Yes, I mean now.
Okay, that's actually true. That's that thing. That's actually true. Because maybe they are concentrated in another part of the, maybe in the urban areas or in the places where people are fewer.
And service is not available.
Rural, where there are more people.
Exactly. And it is very expensive. It's only the poor people see that they cannot afford.
Thank you. That's another thing. Cost.
Okay.
Yes.
Those are interpretation now. But if you look at this also, hospital availability and doctor availability, there's correlation, of course, positive correlation. Then annual per capita income and doctor availability. Yes. Then population density and doctor availability, of course, is this one is correct, is minus. The sense that if the population increases, the doctor availability will reduce. Can you see? So they will move in opposite direction. It's negative correlation. Then this one is annual per capita income and hospital availability. Of course, even though it's a small correlation, of course, if the income of the society increases, we have more hospital. Then population density and hospital availability. Density and hospital availability, where maybe as a population increase, many people will bring hospital there. You know, many people go to where there is density now. If like Lagos and Abuja now, becoming highly populated, if anybody want to start hospital, those are the places they will go to, and Port Harcourt and Kano. Then we have population density and annual capacity per capita income. What I just want to, why I did this one is not because I want to correlate them. It's just for you to see when you run a lot of many bivariate correlation together at the same time. This is what it gives you. The way you give it. So if you look at it, you have done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 correlation. You don't know. You have done 10 correlation. Are we together? If you remember, are we together? That you can, if you remember when we, yes? Is there anybody?
Yes, sir. No, just replying. I said yes, sir.
Yeah, if you remember when we discussed during ANOVA, and it's not even only ANOVA, when we talk about even sample size set, how many times can we pair 3 things? You know, for you to pair 3 things, if you 2 things, 2 items, what do you say? 2 items, you only pair once. That's why as you are doing this thing, if you look at it, each of them occur in pair. This one look more like a, if you remember Magna Barca, right? 5. This
yes.
one I to explain Magnema Barker. Yes, I mean now. How many? Because we have 5 variables. How many times can you pair the 5 variables? Because if you by variate, you are doing correlation between 2 variables. So 5 is 10 times. If you remember 3, if there are 3 variables, it's going to be 3 times. If there are 4 variables, it's going to be 6 times. Since there are 5, 10. Okay, if you want to prove that, go and run it now and remove population density. Remove one of them and run it. You're going to see that you're going to, if you can't, you're going to have 6. No, it's 10 now. Okay. You don't need to even, why did you stop sharing? Hello?
Hello, sir. Sorry, sir. I thought you wanted me to.
But you didn't need to, you don't need to stop, share the result again. You can go to analysis through that result now. You don't need to go to data editor window. You can go to analysis through the result window. Share the result again.
Three times.
Yes. Now, go to, I was counting. Yeah, I said these are 10 now. 10 pairs. Can you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? The same thing you can carry here. So 10 pairs. You
Yes,
10 correlation. Now, go to analyze here. You can access analyze here. Yeah, go to analyze here. Go to that correlation. Correlate. Bivariate. Remove that last one, that population density. Well, click OK now. Okay. Can you see? Can you see the result now? How many? 6? 1, 2,
yes,
3,
sir.
4,
Wow.
5, 6. Can you see? There are 6 now. Because there are 6 ways you can pair 4 things. So if you remove another one now, go and remove another one. It will give you 3. Go. Analyze again. And remove another one. Are you there?
Yes, I am.
And go to analyze again. Why is it slow?
So which one do I remove?
Just remove the last one. Just remove the last one. Click OK. Can you see now? It's 3 1, 2, 3. So if you remain 2 now, it's only one pair, one it will just give you. Because they're different, because in the correlation, the bivariate correlation, you are looking at 2 variables at the same time. So when you put in 3 variables there, you say, okay, variable 1 will correlate with variable 2, variable 1 with variable 3, 2 with 3, so 3 pairs. If there are 4 now, 4, the last one you did, let's A, B, C, D, A and B, A and C, A and D. Then you now come, that's 3 now. B and C, B and D, that's 5. Then C and D, that's 6. That's when you are dealing with 4. They give you 6. If it's 5, it give you 10. If it's 3, it give you 3. If it is 2, it give you 1. Does it make sense? Now, just go back to the analysis.
I didn't get that last one for 4. You said A and B.
That's what you did now.
Okay.
Scroll up now. Scroll up to look at the result of the 4. No, you don't need to analyze now. Scroll up the result. It's in the result now. Don't go to analyze. Scroll up.
I'm there, sir.
And this is the result. It's okay. This is when you are 4. So how did they pair together?
There are 5 here.
There are 5. Okay, this is the first one. And this is first one.
Yes, sir.
And this is first one that are 10 results. If you say this is, just wait.
Okay.
This is A. Let's say this is group A.
Okay.
Group B. Group C.
Okay.
D. And now group D variable and E. There are 5.
E. Okay.
How many ways can you pair them? You can say A
and A
and B. A and C.
B.
A and D. A and E.
D, A and D, A and B.
B and C.
B and C.
B.
B and E. B and E.
B
and D
and E.
E. That's
And
E.
C.
You can have C and D.
And D.
C and E.
C and E.
And D, C and E.
And D and
they can have D and E. So that's 1, 2,
yes.
3, 4,
So
5,
count.
6, 7, 8,
Go to 10.
10. Okay, wow.
Can you see now?
Okay, I now understand. Okay.
So different way you can pair them.
Yes,
so that's
sir.
why it give you this 1 to 10 results. If you scroll down and go to the something, if you do it the same thing, scroll down to the next one, which is for 4. Scroll down, that other result for 4. Scroll down. Yeah, you are there. In this case now, if you look at it, there are A, B, C, D. So if you write it, it's going to give you 6 options. Because this is A, B, C, D. It's going to be A,
B, A, C, A, D.
A, C,
A, B, A, C, A, D. That's 3.
A, C.
1, 2, 3.
And
then there's B, C,
C,
B, D. That's
D,
5. 5.
B, D.
Oh, yes, it's 6.
And
oh, wow.
And C, D. Make it 6.
Yes.
So that's the combination.
Yes,
so if you scroll down, the last one, which is 3, scroll down. Because sometimes, and the last one, which is, if you say is A, B, C, D now, A, B, C. So that one will be A.
You have A and B, A and C, and B and C. Okay.
That's why it's giving you the 3. If it is only one, it's going to be only one pair now. You cannot, if you are 2, it's only one way you can pair them. That's why you do correlation. So that's just it about that. You can, the only thing I want to do, go to analyze. Correlate, click on partial. So move doctor availability and move population and move per capita income. Like you want to correlate between availability and per capita income. Controlling for hospital availability. Okay, no, wait to. No. Is remove that doctor availability, death rate is death rate you are supposed to put that. No. Okay, death rate. Okay. Remove doctor availability and put death rate.
What about the annual per capita? Do I leave it there?
Yeah, I just want you to control for something. Don't worry. You can put the annual death rate, annual per. Okay, you can leave it. Annual and death rate, and now control for population density. And click OK. Click OK.
I clicked it, sir.
If you look at it, is by you do between annual per capita and death rate, but you control for effect of population density. This partial correlation. Can you see?
Yeah.
You understand? This is partial correlation. So if you go and check the correlation between annual per capita income and death rate now, you know this one is giving you minus 0.143. Scroll up, go and check the initial value before you control for this thing. Go up, let's look at correlation between annual per capita income. I think it's in minus 0.2 something. Okay, so okay, yeah. Annual per capita income and death rate, Abi?
Minus 172.
Now is minus 0.
Minus 0.17.
Now is minus 0.143.
Yeah,
so it has removed effect of population density. You know, sometimes when you see correlation, it may be, that's why correlation is you cannot just base your judgment on it, because it doesn't really mean that thing they have anything much related. It may be some other thing that are confounding, that are related to both of them. So any question so far? I will stop there for today. Any question? You can stop sharing.
Yeah, I hope you will send the slides to us?
Yes, I will do that. I will do that.
All right, thank you, sir.
Yeah.
Then the videos that are not opening. What do I do?
Let me just stop recording now so that
the videos they open.
No, wait. Before that one, is there any question concerning what you have done? If there is no question, I can stop recording and now attend to those issues. Okay. Yes. Any question? No question, right?
Hello.
Yes, I can hear you.
Hello.
I can hear you.
I'm just okay. I'm just wondering about this nomenclature of point biseria and biseria.
Okay.
Which many of our fellows and examiners will not appreciate for a candidate to correlate a quantitative variable with a categorical variable. That candidate will fail the exam.
But I don't think completely like that, sir, because well, it depends. It depends, because there was a time a lady in dental in Lagos. I was analyzing. After analyzing, they want to do biseria. I was so impressed that she understand what. So you understand? I say yes, this is. So I did it for her. So maybe you have been doing it. The only thing is that and they have been going scot-free. Sometimes some of this thing, many people they know about it too. It's only that not to the same degree for everybody, and the examiner also differ in their attitude and their personality. Some people, examiner just want to, even exam, they just want to show that they know this thing. They will not use to fail you. They just want to, when they ask you, if they know new, if somebody just knows new thing now, you go and back this, or to go and show for to his candidate, and they want to show that they still know more than you. So, but it's bad that some examiner will fail somebody based on the fact that the person does not know something that you yourself just knew 2 months ago. No? If people think like that, there are some things that, though I know there are some things that are very basic, you can fail people for. But there are some things, I don't think anybody should. Though you are right to a certain extent, because some people, when they don't know, instead of them to even learn from the student, they believe that if they don't know it, that it doesn't exist. It doesn't exist. It's a rubbish.
That's it.
Hey, that's a major issue. But many people, yes. Okay, so that's just it.
It takes humility for people.
I think we'll go. Okay. Any other question?
Yes, sir.
Okay.
I have one question.
Okay.
I beg pardon me if the question sounds very stupid. Okay, so if I am trying to attribute maybe a change to a particular intervention, and I know of other possible, confounders that could have, led to the same result.
Yes.
If my intervention did not happen. So
Yeah.
if I'm structuring my questions now in the questionnaire, it means that I have to also ask questions in the questionnaire.
Exactly. That's what they talk about. Exactly. That's why they say you do extensive literature review. Those things you see that may be a factor, you collect data about them. And if you don't collect data about them, you cannot remove the confounder effect.
Okay.
It's only when you collect data about them you can remove the effect from your study. Yes, that's
okay. Okay. Thank you very much.
Welcome. Any other one? Okay, don't worry. Okay, go on.
Okay, I actually have a question. Now that from Dr. Jane has mentioned, I just thought about something. You know, the way before we decide that we want to go ahead and the logistic regression, for example, you know how we use the P to decide, when you have that. Now in correlation, because I noticed that of course, with the partial correlation, it looks a bit similar. I know correlation is about, of course, the strength of the association, but is there something like that? Is where you now decide that, I want to do a partial correlation. That is after you've done the correlation, for example, and you see, okay, yeah, you see that P is useless correlation. Like, how do you now decide, okay, this might be a confounder? Is it based on that literature review, as you mentioned?
The way, why, if you look at it, even that partial correlation is not so popular. You know, it's not everything that is academically sound that is practically sound. It's not, when I say practically sound, whether let me say, maybe operationally sound, let me use the operationally sound, it may be practical. That is, when I say operational, like for example now, Jane is a development worker. You discover that when we are talking of research, because I've been privileged to be in the academic environment and development environment, I see that what is academically sound is different from what they are looking for. That's why if somebody that is good academically can write paper and give it to these people that do development, it doesn't answer their own question, but they are looking for something else. Do you get it now? And the way most of the time, they have done something, they want the effect, they want to know the effect of what they have done to these people in the community. They are more, that is what is on ground. But sometimes they will do something based on available funds and the practicality of it. Whereas the academic may say, oh, nonsense, how can you do this? So the issue there is this correlation of a thing is, talking about partial bivariate is more like descriptive, academic exercise. Because along the way, people get to know that even when something correlates, even the one that correlates, even after you have removed what you think is confounder, it doesn't even show you that whatever remains has effect or anything. So it's more like screening exercise, just in analysis. You discover, if you follow analysis very well, you discover that most of the time people don't make any concrete decision until they have done something like regression. Because doing chi-square is more like screening. It's helping you to narrow down your area of focus. Even when you do correlation, can you see that this one correlate more here? You're not okay. So that we can explore it later. It's more like screening. So because if you do, it's just like when you do chi-square, you can have many variables. You do this one, education is significant, this one is significant. If you just go and conclude based on that, you may end up in the ditch until you do regression. Something you discover it's significant. When you do regression, you discover that multiple regression is not more significant. just like what Jane said, if you have not collected data on those factors that may be sounding as serving as confounder, you now just you end up with that, with what you get from your chi-square or from your correlation, whatever. You are just wasting time. And that is why I would know what when we get to regression, regression is quite interesting. By the time we get to tomorrow, you're going to see your eye will be open to a lot of, it will be like revelation. Your eye will be open to a lot of things. Some people who do work, it may sound, in fact, some people show in University of Nasarawa State University here, when some people in the, what do I call it, social science, they brought some, in my office, they brought some research, and they run the analysis in the university to actually know some factor that determines some things so that they know how to run the university. But when they finished the analysis, those guys, they were showing me this, I just laughed. I laughed because all those factors they listed here, they didn't contribute up to 20%. So if they give recommendation, and at the end of the day, they spend money, they are wasted their money because they cannot, whatever they have addressed cannot address up to the 20% of the problem. It's a waste. So when we do regression tomorrow, you will be able to understand when we talk about coefficient of determination. And that is why this issue of, if you look at the partial correlation, is not common. Nobody, how many people does it? So people just do very correlation, more like screening, and now go to more reliable thing. Because instead of me to be doing partial correlation, I would rather go and do regression. I don't know if you understand. I've answered your question now. I will go and do regression that will solve the problem. It's not by doing partial correlation. The partial correlation also may not still solve it. Whatever it gives me, I cannot see it because correlation does not mean causation. It doesn't. It's not like regression that is looking at relationship and looking at how you can determine one from the other. Though it's very useful because even in interpreting regression, correlation and regression, they go together. Yes, I mean, it's just like somebody, well, it may happen. I just want to say something. It's just like two people that marry. That is a relationship, is that not so? But before they marry, there must be association. At least when they were cutting, they meet somewhere. There's no way you can have a relationship without association. Just like for relationship regression to come in, correlation has to come better. Not everything that correlates can have relationship. Yes, I mean. Okay. Yes, not everything that correlates, but if two things have relationship, automatically, of course, they will have to correlate. Because that correlation will be there before they can have relationship, but not everything that correlate have relationship. So the example I use may sound so because in India, they can bring wife for somebody that they never met before. In the old day in Nigeria, they do that also. You just bring somebody you have relationship now, no association before. Just get married to somebody you never met. You do happen, it's still happening in India. Okay?
Thank you very much, sir. So I wanted to just ask one final one, because I know that I see this a lot when I see objectives. When they tell you to identify factors, are they telling you to do, for example, a bivariate or regression?
Of course, now for you to identify factors. Thank God, Akogu, let's see your face. For you to identify factors, is the regression you do is not bivariate. No, bivariate. When they say bivariate means two variables. All other analysis like chi-square, TS, although they are bivariate in the sense that they are looking at association between two variables. Yes, even correlation is the same thing. It's two variables. It's the regression that has both two and multiple. Regression, simple regression, two variables. Multiple regression, many variables, but one hardcore, and many exposure, many independent, one dependent. You're going to see by tomorrow when we start unfolding a regression. That is why regression is the answer, because the factor they are talking is regression you can actually use to determine the factor. Okay, I think we.
Thank you very much.
Go other question.
No,
Yes.
If I run,
yeah.
if I run,
Before
okay.
we go to the video, there's no opening. Before we go to the video, there's no opening. I need to clarify something about this partial correlation.
Okay.
The partial correlation, is this something that is independent on its own that you can analyze, or you first of all do another analysis, then you want to use the partial correlation to eliminate a confounder,
Okay.
just like the way you use regression to eliminate?
Yeah, the issue there is that it's just a step further, as if it's going to do the work of regression, but they cannot do it. The issue there is that
a step further from where? Because you cannot. You cannot. Just a minute. You cannot use it for bivariate because bivariate is only two variables. So bivariate is two variables. So where did the third one come from?
Wait, that's what we are saying. You say you are looking at correlation between. I gave an example now. Somebody's attendance. You know, in school now, you have to write your name because they want people to attend class. Attendance rate and score. You want to see, is there any correlation in there? Maybe those people that have about 80%, 90%, are they more likely to score more? If you are correlating the mark, you may see that correlation is strong or whatever moderate, but there are a lot of other things that may affect it. They are confounder in the sense that the IQ of individual. There are some people, they don't attend much, but they are more intelligent than the other. They will actually score more than others. So two people that attend have the same attendance rate. The other one is more intelligent, will score more. That is a confounder. Then the time you study personally, the people that study more, apart from attending the class, apart from being intelligent, if the people study more, you more likely score higher. So if you are correlating between attendance rate and score, those confounder, if you want to now remove the effect of those any confounder from that correlation, you just add that variable you want to remove effect from. That's what they call partial. You get the picture now? Called partial correlation. But while partial correlation is not popular, it's not popular. It's because people do, instead of people doing that, they just use correlation to scan. Is there any association? If they want to do any further analysis that make them to take tangible decision, people go for regression. They will not go for that partial correlation. Go on, sir. After all, the correlation, because in correlation, you don't say one is outcome, one is dependent. One is outcome, one is exposure. There's no dependent and independent variable in correlation. So because of that, it's difficult to make you use to now say this one depends on this. So that is why doing partial correlation, people don't even do it. They would rather go and do regression. If they already know that, okay, this is a factor, these are factor responsible, they now remove the effect of confounder. I don't know if I've answered your questions.
I think let's leave it like that.
Okay. Don't worry. Maybe you get to know it better tomorrow, because we'll still talk much more about correlation, then we'll move to regression. Jane, you are asking a question. You have left the place. Okay.
The video that I cannot
let
open.
me stop.
Can I share it again?
And wait.
Okay, so
you have a question?
Yeah, so my question is this. By the time you run the correlation to remove the confounders, after removing, if you notice that there's no significant change, then it means that you have wasted your money conducting that assessment in the first place.
Okay.
Should I conclude at that point, or is there any other thing?
No, are you talking of regression or correlation?
I'm talking about correlation now, because I see that with correlation, we're able to control for some things to see if there's a significant difference and all of that. So I'm saying if you run the correlation, you remove the confounders, that's you control for the things that would have given you the same change. And at the end of the day, you discover that what you have done, your intervention has no impact after removing the confounders. Should I conclude at this point, or is there any other analysis I could do that will determine finally whether there's an impact or no impact?
Okay, let me tell you something.
Should I rest my case at this point, or is there still one more analysis I could run before I conclude that?
No, I've already said that you were not listening when I was answering Dr. Ekobo's question. You left.
Okay.
Yeah. I said that you don't take decisions, you take decision about effectiveness of your intervention by correlation.
Okay.
Yes, I'm not. Your correlation is just one of the analysis that even you don't even take it based on chi-square, t-test, all those things. And more like screening in the process of judgment, making judgment. It's just like in the law court, they do before they judge, they go through the processes. So you grab this party, you tie a lot of things together. So correlation is just one of the analysis you do along the way, but it's not analysis that give you the final judgment. That's why even the one that is closer to the when it comes to the confront somebody is playing the video. So now the one that I usually use even to make a conclusion most of the time is the regression. You get the picture now, so you don't use correlation. Now there's another aspect of the question you were asking. Research, the study you are doing, is not a solution. Research is not a solution to problem. It's only that it gives a dependable solution. It gives recommendation. Yes, I mean now. So when you do an intervention, you not carry out study, you did not find that there's no. It's not as if that is the problem. People now you are finding out. Your research is to find out that this method that what we did is actually so. For the fact that you find out that it's not effective, it's a finding. Because if you now find out next time you will not do that type of thing. Do you get the picture now? So if you cannot say you have wasted your effort by doing this. No. Okay, you have done it. What informed you doing it? You have done it. You just want to say, okay, you want to find out this thing, is it actually effective? So it's for you to know if it's effective or not. If it's effective, how effective? If it's very, very effective, oh, you are happy, you want to deploy the same method. But if it's effective, but not too much effective, you want to see how you can improve. Which method can you use to improve on it? If it's not effective, you know that this is not what to do again. I don't know if you understand now. Because when people think like that, we are wasting our effort. That's what makes them to now dodge results. But I see in many exams, when people are preparing for exam, after your final say that shows that all your effort is wasted. That is rubbish. And it made these people, especially those people that say they are doing intervention, it did not make them to dodge. Let me tell you, negative finding is a finding. If you find out that this thing doesn't work, it's a finding, good finding. If you have done the work very well, especially you may review if the power is there, that the power of the study is very high, the sample size is big enough, and you look at your protocol, you have done the right thing, that shows that that is not effective. But many a time in exam, you see people talking, many examiners and supervisors, they will tell people, they say that shows that all those things waste effort. But okay, if it's not that it's not a waste effort, why is he doing the research? Because the research to really know that this method is effective or not. And the answer can be yes or no. Must the answer be yes? Even the last one I analyzed, all of them got a result. I'm telling you, all of them that said they did the intervention. Iguilo, they are your friend. The nonsense they did, and they not say intervention.
Yes, okay.
With deceiving people. That is why I like what this really said. There are three kinds of lies, damn lies, and statistics. A lot of people, what people publish is lie. Many people, okay, by the time they finish the exam, they go and publish the result with their supervisor. And they will be quoting Professor so and so. This, not know that it's lie, they tell there. And the person also, no? After you are the product of lie, everything lie. So who are we deceiving? And at the end of the day, if you take decision based on whatever they are produced, you are wasting your money. So to me, if a candidate came, you do the survey with D5 and you pass. On you failing or passing should not be contingent on whether the result is positive or negative. Even if the result is positive, you find something good there. If you did the work chabily, it's not good, you should fail. But if the result is negative, you do the work very well, you should pass. That's just it. I think we can stop here. There's no other question. Let me stop.
The intervention I'm trying to assess, a clinical trial has been done with this intervention. And through that clinical trial, it was shown, you know, that thing is effective, you know, and is capable of reducing malaria mortality and morbidity by 75%, which I think is too ambitious or too high.
Yes.
You know, so with that kind of published work, now I'm a bit jittery with, you know, the work.
Yeah,
the
don't worry.
No,
let me tell you something. Be pragmatic and straightforward. All of that. Let me just pause now. Let me just pause.